Hello, people from the future. Welcome to Normalized Nerd. Today, I'm going to talk about the forward algorithm in hidden Markov models. It's a very elegant technique to efficiently carry out the long computations in hidden Markov models. But apparently, many people face trouble wrapping their head around this concept. The reason being, they don't try to reinvent this forward algorithm trick for themselves. So my goal for today is to make you feel that you could have also invented this trick on your own. So without any further ado, let's get started. To begin our journey, we need a hidden Markov model, right? Let's have a simple HMM with two hidden states, rainy and sunny. Green arrows represent the state transitions. The two states represent the weather on a particular day in a hypothetical town. And as the observed variable, we have our friend Jack's mood who lives in that town. He can have two moods, sad or happy, and Jack's mood depends on the weather, and the relationship is shown by these red arrows. Let me write the transition and emission probabilities. The diagram looks a bit messy, so I'm just gonna write the transition and emission matrices separately. Let me also write the stationary distribution for the hidden states. If you have watched my previous videos, then you know how to compute pi from the matrix A. Feel free to pause and verify this result. Okay, so now we are ready. First of all, you should know where the forward algorithm is needed. Suppose we have an observed mood sequence like this. On the first 2 days, Jack was sad, but on the third day, he was happy. We want to know what is the probability of occurrence of this particular sequence given that we know the parameters of our hidden Markov model. Well, the parameters are nothing but the transition matrix, emission matrix, and the stationary distribution. Mathematically, we will write this, where y0 denotes sad mood and y1 denotes happy mood. To compute this, we need to consider all the possible sequences of hidden states that might produce this observed sequence. Take this sequence for example. On the first day, we have rain followed by 2 sunny days. Let's compute the probability for this case. First, we have the probability of rainy day multiplied with the probability of sad mood given rainy day, then sunny day given rainy day, and so on. Yeah, I have denoted rainy state using x0 and sunny state using x1. Notice that we can fill the terms from matrix A, B, and the stationary distribution pi. If you face any difficulty in understanding this, then I would highly recommend you to watch my previous video where I have covered all the basic things of hidden Markov model. But this long product only gives the probability for this sequence. Can you find how many such sequences are there in total? Well, we have got 3 places and 2 choices for hidden states. So there exist 8 possible sequences of hidden states. Let's visualize them. And here are the probabilities corresponding to each one of them. To find the probability of y equals y0, y0, y1, we need to add all these 8 long products. Yeah, if you are gonna follow this naive way, you have to do this huge calculation. If you count the number of multiplications, you will find it's of the order of t times n to the power t, where t is the length of the observed sequence and n is the number of hidden states. That means the time complexity increases exponentially with the number of hidden states. This is the reason why we need an efficient way of computing this. And the efficient way is the forward algorithm. Now we are ready to rediscover this trick by ourselves. If you notice carefully, you will find we are computing many products more than once. For example, we are computing this product 4 times. Same goes for this one. You will also find repetitions here. What if we can somehow store the results and use them in the future? But to store the previous results and use them in the future, we need to find some recurrence relation. Well, a recurrence relation simply means we can find the nth term by using the terms that came before it. Those of you who are familiar with dynamic programming must be very excited right now. So let's see how can we introduce recurrence relation here, and hence dynamic programming. So this is the thing we are trying to find. The key point in dynamic programming is to divide a big problem into subproblems. We can divide this into two cases. In the first one, we are taking the sequences ending with x0, and in the second one, we are taking the sequences ending with x1. Please notice that I have left first two places blank. That means on the left, we are considering all the possible sequences of length 3 ending with x0, and on the right, sequences ending with x1. For a moment, imagine that we know the probabilities corresponding to these two cases. We are going to denote the probabilities using alpha. The subscript of alpha denotes the length of the sequence, and the subscript of x is for different states. So we can find our answer just by adding these two cases. Nice. But how to find this alpha terms? Well, we can decompose them even farther. For alpha 3 x0, these two cases will arise. The sequences of length 2 ending with x0 and with x1. According to our notation, there will be alpha 2 x0 and alpha 2 x1. But how can we use these to compute the parent node? Feel free to pause and think about it, because this is the most important realization here. We just need to multiply the transition probability from step 2 to step 3 and the emission probability at step 3. Remember that we can do this because of the Markov property. In other words, step 3 depends only on step 2, not on the previous steps. I hope that makes sense. We can do the same thing for alpha 3 x1. Isn't it elegant? Now let's focus on alpha 2 x0. This again can be found by taking two cases, alpha 1 x0 and alpha 1 x1. I hope you can write the formula for the parent node by yourself this time. The logic is same as before. But what about alpha 1 x0? We can't decompose it any further, and we don't need to. We can find this from our known parameters. Probability of x0 comes from the stationary distribution, aka pi vector, and probability of y0 given x0 comes from the emission matrix. The same applies for alpha 1 x1. So let's complete our tree. If you look at the tree now, you can see that every level can be computed from the levels below it, and we can store the result at each level to use them in the future, implementing dynamic programming. And the base cases are the two leftmost leaves of our tree. Let me show you this more systematically. It is clear that alpha t xi can be found from alpha t minus 1 x0 and alpha t minus 1 x1 like this. Here you might ask, okay, but what if there exist more than two hidden states? Well, that's simple. Just compute alpha t minus 1 for all the xj's, where n is the number of hidden states. You can imagine in the tree, every node is having n number of children. And that's our recurrence relation. What about the base cases? Here they are. At last, to compute our final answer, we need to sum the alpha t's for every hidden state. And there you have it. You have just discovered the forward algorithm. Did it feel intimidating? I don't think so. Now we should compute the answer that we are looking for using this algorithm. So let's turn on the autopilot. And here is our answer, 0.1344. If you count the number of multiplications we performed here, you will find it's exponentially smaller than the naive way, which is awesome. So that was all for this video, guys. If you enjoyed this video, please share this and subscribe to my channel. Stay safe and thanks for watching.